Alright, so good morning everybody. We are Design Team 9 and we are going to be talking about how to grow a diamond. My name is Afif Al-Sanan.
I'm David Star.
I'm Mohamed Rashid.
I'm Jessica Oaks.
And I'm Thomas Rex.
Before we get into the nitty-gritty of how to grow your own diamond, we wanted to talk about how this is important to both our sponsor and our design project. Diamond growth is done right here on campus by Fraunhofer, and our project is actually measuring how good a diamond is. So understanding how a diamond is grown and where impurities and imperfections can come in during the design or the growing process is very important to our project.
So here's an overview of what we're going to be talking about today. I'm going to start with the natural and synthetic diamond.
Then I'm going to talk about chemical vapor deposition.
I'm going to talk about the advantages and disadvantages of different processes.
I will be explaining the diamond structures and its impurities.
And I'll be talking about the application and properties of them.
So I would like to start by talking briefly about the natural diamond. So diamonds are made of carbon atoms and they are formed about 100 miles below the surface, which in that part it is very hot and there is a lot of pressure, which is the type of conditions that are needed for the diamond to be grown. Now the diamonds that we see at the surface are actually brought by volcano eruptions. So when eruptions reach the surface, they build up, creating a mound of like volcanic material, and the diamond can be found within that material. Now natural diamond is not 100% pure. There are a lot of defects, and the defects are actually frequent in diamond, and that is why it is rare to find like a big pure diamond crystal, and that is also why it is expensive. Alright, so synthetic diamond. Synthetic diamonds were first developed in the 1950s, but only recently they have been like available for commercial use. And there are several methods of growing diamond, but we're going to be talking about two main methods. The first method is HDHP, which is high temperature, high pressure. And the other method is chemical vapor deposition. So in high temperature, high pressure, graphite can be turned into diamond by applying high temperature, high pressure. And just to give an idea, we are talking about a temperature of 1400 degrees Celsius and a temperature and a pressure of 5 gigapascal. Now the process of HDHP takes 7 to 10 days to be completed, but once it's completed, the synthetic diamond would have the same crystal structure as the natural diamond. And another use of the HDHP is for diamond treatment. It is used to treat the optical properties of the diamond and also to enhance the color. And as you can see here, this is a picture of a natural diamond where its original color is brown because of the impurities and the defects in the diamond. And by applying HDHP, we can turn that into a colorless and more pure diamond.
Chemical vapor deposition, also known as CVD, is another way that's used to grow diamonds. This is the method that our sponsor uses. Previously, when we've talked about diamonds, we've assumed that everyone has a general understanding what a diamond is. The technical definition of a diamond is any material that is mainly composed of carbon with sp3 bondings. What CVD does is it adds carbon atoms onto an existing diamond structure. This maintains the bonds and allows you to grow a diamond upon an existing diamond. Chemical vapor deposition is a process by which chemical reactions between a vapor and a substrate are used to grow more material. The type of CVD that our sponsor uses is monocrystalline diamond growth, which means that it starts with a complete diamond substrate. So you have your whole crystal alignment, and the diamond is grown up upon that. Chemical vapor deposition can occur through a variety of chemical processes. There are two specific things that need to remain constant, though, even if the chemical reaction is separate, is different. There has to be a high concentration of hydrogen in the gas, and there also has to be some type of carbon source in the vapor that's being used. This illustration shows roughly what happens during CVD. Gas is flown into the chamber, and then plasma inside the chamber causes the molecules to split, resulting in charged particles. Starting on the left and moving right, the gas that has been ionized reacts with the surface, carbon is deposited on the surface, and the remaining hydrogen is able to combine and then be released. This allows for carbon to be added onto the diamond, upon which more carbon is eventually grown. To give an example that will hopefully illustrate how this process works, we're going to talk specifically about an example that uses H2, which is hydrogen gas, and CH4. The first picture shows how hydrogen gas is first split into hydrogen and CH3, and the hydrogen can bond with carbon atoms. When the hydrogen bonds with the carbon, more hydrogen can interact with this hydrogen. This combines to form H2, which is then evaporated from the substance. Essentially, hydrogen can bond with the carbon and then be deabsorbed, so hydrogen's added and then subtracted. Nothing happens, essentially. However, the first three images in this diagram show how when hydrogen is removed from the existing diamond structure, CH3 is able to bond. If CH3 bonds in two adjacent spaces, and then more hydrogen in the atmosphere, in the air, combines with one of the hydrogen atoms in the CH3 to form CH2. The CH3 and CH2 are able to combine so that there is a strong bond between the carbon atoms. The bottom picture below, at the very bottom, shows how the carbon that has been deposited by the CH3 becomes part of the diamond. This is where the cycle repeats, because this results with carbon atoms with hydrogen bonds that are exposed to the vapor. And those hydrogen bonds in turn react with the hydrogen in the air, and the whole process repeats. The image on the right shows how diamond crystal can be added upon, each step showing how it can be added and maintaining the crystal structure.
There are specific advantages and disadvantages to each process. CVD over HTP has a number of unique advantages in that you can control a lot of the impurities that goes into a diamond, just define its color, electrical, optical, and pretty much every other property that we have. CVD is also grown on a substrate, which you can define the area of. You can make a very thin but very large sheet of diamond. You can use various substrates with the same machine to change them out. And it's a very low pressure process compared to high temperature, high pressure in high kilopascals compared to 5 picopascals. And this picture here is showing you several different setups for the CVD process. You can get simple where you just heat up your sample here with a filament, or you can get advanced by hitting it with microwaves to turn it into a plasma. But it does have some disadvantages. If you want to make a big honking diamond to maybe go on jewelry or a ring, you want to probably look more towards high pressure and high temperature, just because it's industriable. This is a company out in Denmark, and you can see each one of these is a high pressure, high temperature diamond growing station. It's also, CVD is also a very slow process, taking approximately 900 hours, which is right around 35 days, compared to 7 to 10 days for high pressure and high temperature. And the only property that high pressure, high temperature has over CVD is the fracture toughness. So if you're looking to put diamond, I'd say like drill bits or cutting materials, having your diamond blade fracture prematurely is probably not something that you want.
So we've been talking about diamonds and how there's tons of impurities in them. And so these are some examples of the impurities you can see in diamonds. The top left picture shows perfect structureless of a diamond. And top right, we have interstitial impurity, in which an atom that is not common in the diamond structure can get into the interwebbings of the lattice of the crystal structure, thus forming stress or expanding it out to create the impurity in the diamond. We also have cation vacancy, where one of the lattice structures of the diamond ends up being removed, thus also causing stress and forming impurity. Same thing also happens with anion vacancy. There's also substitutions of lattice structures as well, where crystal particle that normally fits into the lattice gets substituted for another type of atom or a certain element, and thus also creating an impurity in the diamond. And at the bottom, it can also be different structural sizes. As in here, what it should be typical and small size will also be larger. And then here also, you'll see that it's also out of alignment to the normal structure of the crystal lattice. So how impurities occur after, how occur and affect the diamond. When the crystal structure is grown, once an impurity starts in the crystal structure, as it keeps growing up, that impurity will also grow up with the rest of the diamond. So when you think like it would just grow there and then it'll be fine afterwards, you can probably just cut it off. That's not the case. So once an impurity starts in the diamond in the growth process, it will also stay in the diamond all the way through. Impurities occur in about 1 parts per million lattice structure of it. So every million lattice part that you look at the diamond, there's about 1 defect in it. Different diamonds become different colors due purposefully or accidentally due to the impurities in the diamonds. Pink diamonds usually come from structural abnormalities due to plastic deformations. The yellow ones usually occur at a nitrogen base, which if it gets spread out throughout the diamond in the growth process, it will turn to a yellowish tint. And then boron will, if it gets in the lattice structure, will usually give the diamonds a blue tint. And then here are just 2 different structures of the crystal. Monocrystalline, as Jessica was explaining before, is a diamond-on-diamond substrate, where you'll have the diamond substrate and you'll take diamond particles and add it on to grow it up into a single mono crystal structure. In terms of solar cells, it's more efficient, though the structure and making of it is usually more expensive. Polycrystalline is when the substrate is not a diamond. It can be silicon or some other type of substrate, but it has to be pre-treated beforehand with some type of powder, that diamond powder particles. That way when you do put the diamond material on it, it's able to grow up from that substrate. It can't just grow right off of the silicon. You need some sort of pre-treatment for it. Polycrystalline usually gets really big, honking type of diamonds, also like in terms of high temperature, high pressure. So there's a large area, discs, and coating. Polycrystalline usually handles harsh environmental conditions. It's used for high speed. There's examples that are used for high speed, like warfare use and other stuff. And it's also less efficient in terms of the solar cell use.
So now I'm going to talk about the different properties of diamond. First we're going to talk about the electrical properties. First thing you should know that a pure diamond is actually a bad conductor, but as the temperature rises up, the conductivity of the diamond will increase. Secondly, pure diamond has no magnetism, but a synthetic does. This is because of the presence of impurities in it, such as cobalt, nickel, manganese, or iron. Diamond also possesses triboelectricity property, which means that when it is rubbed against hard surface such as glass or hard rubber, it will generate positive charge. Right? And then diamond also has the capability to generate photocurrent when it is irradiated by UV light of the wavelength from 210 to 300 nanometer. For the optical properties, pure diamond is colorless, but the diamond that we see every day has color blue, red, yellow. This is because of impurities, like Thomas said before. Diamond also have high refractive index. In fact, it has the highest among any other transparent minerals. High refractive index will make it having high reflectivity. So if especially designed diamond and process, it is capable to reflect all the lights that is shining through it through all the sides. Next one is it has a high dispersion coefficient. Again, it is the highest among any other transparent minerals. High dispersion will make the better spectroscopy result, which means when we shine a white light, it will disperse into rainbow colors. And because of this too, it makes diamond is a very pretty object.
Alright, so what is diamond doping? So the pure semiconductor are neutral. They contain no free electrons. And even with the application of thermal energy, only few bonds of the pure semiconductors are broken, which results in a relatively small current flow. Now, a much more efficient way of increasing that current flow is by adding impurities to it, to the pure semiconductor. And the process of adding the impurities to the diamond is actually referred to as diamond doping. And as we can see in the picture, we are adding other atoms to the carbon atoms in the diamond to increase the impurities. And through doping, we can use diamonds as electrodes. And a good example of diamond doping is the boron doped diamond, the BDD, which is simply just diamond is being doped with boron to increase the conductivity of the diamond. And another example is which is actually a new method of doping, is by evaporating the carbon molecules of the diamond onto hydrogen-terminated diamond surface, which actually increases the conductivity of the diamond significantly.
So lastly, I'm going to talk about the application of diamond. So when we heard of diamond, the first thing that comes to our mind is jewelry, such as diamond ring, necklace, bling blings, and also some random stuff like diamond-studded skull over there. And then diamond can also be used as abrasive. It is used as cutting tools and also used to engrave stones and hard surface like engraved on a diamond. It is also used in form of slurries. Slurries means it is a semi-liquid mixture that consists of diamond powder. Consists of powdered diamond in there. It is used for polishing purpose to polish ceramics, metal, and many more. Diamond also can be used as electrode, as Afif presented just now. It can also be used as windows in the X-ray machines and lasers, where thin membranes of diamond is used to close up the holes in the machine itself. So in future, there's a high possibility that diamond can be used in medical device and surgical tools, such as LASIK procedure to repair eye defects. There's also a possibility that it can be used in a nuclear fusion reactor, which is a new clean power source in the future, because the reactor needs a material that can withstand very high temperature, and diamond is capable of doing that. And lastly, it can also be used as computer parts as well. In summary, we already talked about the natural growth of a diamond, and then we talked about a synthetic diamond that two different types of synthetic diamond, which is high temperature, high pressure, chemical vapor deposition, and also we compare between those two. Then we talk about crystal structure and impurities, talk about diamond doping, and lastly we talk about the diamond properties and the uses of it. Any questions?
Thank you. Are there any questions up front?
So the CVD, you mentioned like 900 hours Which is faster, if you use a resistance heater or a plasma heater? And what's the best way to reduce that time?
Our sponsor uses plasma.
Is it any faster than resistance, or is it just more efficient, or?
I think it's more efficient. I can check.
I mean, we've only seen, we haven't really looked at the differences between the types of ways. We just know that our sponsor uses CBD and plasma, so I'm assuming it's more efficient because there'd be no point in using the resistant one.
It's a negligible time difference.
All right. It's more the chemical process that slows it down. All right.
Any other questions? If not, let's thank our speakers. Team 10.